So I hear there's some questions on the homework, which I'd be happy to address. While I'm getting set up here, I will mention that part of what you need to do with your homework problems is try and match your answers to the answers in the back of the book. Now, a lot of times you'll get the derivative correct, but then actually simplifying the derivative, cleaning it up, is usually an exercise in algebra, and that can be a little challenging, but it's definitely worth your effort to try and get your answers to match the book, because that's part of the skill of this course, is getting good at the algebra. I can remember distinctly when I was in graduate school, I used to do the recitation where the calculus students would go into the class, they would have their lecture, and then on Fridays for like 2 hours, they would all go to this room and get, questions that they had about their homework problems they could ask. And I was the person who stood up there and answered the questions. And so I remember doing a problem for them and putting up the answer, and then later on, like a day later, one of the students went and complained that I had done something incorrect and got all upset and said I shouldn't be up there doing that if I don't know what I'm doing and all this stuff. And it just turned out that it was just algebra that he didn't know how to do. So he made himself look like a fool. And so he just couldn't simplify it. And so, but that's part of the problem. That's part of the challenge of this course, is the simplification of the derivative. So if you have a specific one that you were having trouble getting it to match the book, I'd be happy to look at. Go ahead. 23 or 25. Okay. And this is going to follow with you through the rest of the calculus sequence. If you do more calculus, this simplification is just one of those things that continually is required. And it takes time to get good at it, all right? So, but you have to start with, now, practicing. All right, so you're talking about the product rule, quotient rule? Is that the section you're talking about? Yes. 23 and what?
25.
Oh, yeah. Okay, so let's look at 23. We have y is equal to t sine t over 1 plus t. And for all of these, the instructions are just to differentiate. So what we want here is y prime. We want y prime. Or if you like, you could say dy dt. Just showing you some different notations, right? This means the derivative of y. T is the variable. We do not write dy dx because x is not the variable, right? So we have a quotient, don't we? And because of that, I'm going to apply the quotient rule, which says take the derivative of the top. So here's the top. Take its derivative. I'm going to multiply that times the bottom, minus the derivative of the bottom. Here's the bottom, derivative of it, and then times the top, t sine t, all over the bottom, squared, right? So that's just the quotient rule written out. Haven't taken any derivatives. But I realize that in this first derivative, I actually have a product. So I'm going to have to do the product of rule on that, and I think I'll do that over here on the side. So over here, if I'm trying to take the derivative of t sine t, then that's going to be the derivative of the first one times the second one plus the derivative of the second one times the first one, right? There's multiplications right there. Right, so there's a little product rule that's separated from this answer. What is the derivative of t? 1. So we say the derivative of t with respect to t is 1. Sine t. I don't need to write the 1, but I will. The derivative of sine of t is cosine of t. And then times t. And we said we don't like to put these t's together like that because people can confuse it and think that's a t squared. So I'll write sine t plus t cosine t. That's just this right here. And then I'm going to multiply that times that, and then the derivative here I should be able to take because it's two terms. Derivative of 1 is 0, derivative of t is 1. So I think I'm ready to write the next line. Any questions on that part? All right, so top left of this is in parentheses sine t plus t cosine t times 1 plus t minus, we said the derivative of this is what? 1, right? I'm not going to write it down, but that's 1. And so that leaves just the t sine t. All over, what, 1 plus t squared. And so this is what I refer to as the raw derivative. It hasn't been cleaned up, right? Algebraically, it's not simplified. It's just the raw answer after you take the derivative. It is correct. That is the derivative. There's nothing wrong with that. But everyone in this class should be able to simplify that if possible. So what I'll do is I will realize I've got two terms, right? So I can do like a foiling in that, right? So let me do that over here. So the top left of this, sine t times 1, sine t times t, t sine t, t cosine t times 1 is t cosine t, and then t cosine t times t is what? T squared cosine t. With me? That's just the expansion of this. Then here it's minus t sine t. And that's all divided by the 1 plus t quantity squared. And this t sine t and this t sine t cancel. That's about all I see. Is that what they have in the book? No. No, there's a little more?
Yeah,
they pull out a t? No. T. Let me see. Sine t plus t cosine t plus t squared cosine t all over 1 plus t, that quantity squared. Yes?
Can't you take a t out of the t cosine t and t squared cosine t?
You could. You could take a t out of both this one and this one, but it can't factor out of the whole thing, just out of these two. So what does the book have as an answer? Let me see how much further.
Which problem is this?
23.
Yeah, 23 has a t squared plus t parentheses and then cosine t plus sine t over 1.
Hold on. Let me just look at it. To me, that would be cleaned up pretty good. I mean, there's a couple of little things you could do to this, but nothing major. The main thing was that canceling of the t sine t. That's a major simplification there. This was 2, 4. Oh, okay. All they did was factor out a cosine t. That's all they did. So all they did was say, I have a cosine t here and a cosine t here, right? And they rewrote sine t plus, they factored out a cosine t, or was it a t cosine t? No, it was just a cosine t. I don't know why they wouldn't do both, but then t plus t squared all over 1 plus t quantity squared. So that's the answer in the back of the book. Do you all see all they did was pull the cosine out of this, out of those two? But why not, if you're going to do that, why not pull out a t cosine t? You know what I'm saying?
Yeah.
So I think you could argue like this is good enough. If you're just going to do that, then, you know, but you should practice. You should look at their answer and see if you can get yours to theirs. And then what about 25 was the next one?
I have a question.
Yes.
If you didn't pull out the t cosine t, that would leave 1 plus t.
Yes.
Could those quantities cancel out or no?
What do you think?
I want to say no because it's being multiplied by cosine t.
If you had pulled a t out with this cosine, right? This would be a 1, and that would be a t.
Right.
This could not cancel because you would also need a 1 plus t over here. So if you had a 1 plus t over here, they would all have a 1 plus t, so you could cancel one factor. All right, number 25. I was going to do one like 25 in class, but I was like, no, I want to see how they do with it on the homework. So I was kind of expecting to hear a question about this one. F of x equals x over x plus c over x. Now, anytime that you see A, B, C, D, little a, little b, little c, little d within a problem mixed in there with your variables, those are always assumed to be constants. In other words, they're numbers, but they're not telling you what they are. So this c may as well be a 5. All right? Now, somewhere in the book, I forget where it is, the author does mention that. It's somewhere in the very, very beginning that they'll use this for constants. I think they also say they'll use like alpha, beta, things like that for constants. But you should be clear, it should be clear to everyone that the variable in this problem is x, because it's f of x. All right, so you have a quotient, don't you? You have a quotient. But within that quotient, you have another little quotient, don't you? So let's just write down what the quotient rule tells us we would have. The derivative of this would be the derivative of the top, right, times the bottom, which is x plus c over x, then minus the derivative of the bottom, here's the bottom, times the top, all of that divided by the bottom, that quantity squared. Now let's take a look at those derivatives and see if we're going to be able to handle them. The derivative of x is 1. The derivative here, well, it's two terms, right? So derivative of x is 1. But derivative of c over x, how are you going to do that? You're saying negative, like a negative power?
Yeah.
So there's two ways to approach this. You can either treat this like a quotient and do quotient rule, or you can treat it as a power of x. Now, I'm going to do both ways here. If you were to look at the c over x and find its derivative with quotient rule, it would be derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. Agreed? Derivative of a constant is 0, right? So this would be 0 times x minus derivative of x, 1 times c over x squared, which would be negative c over x squared. That's what that would be if you were to do quotient rule. Now, I would never advise that you do quotient rule on this because that kind of shows a little bit of, I don't know, amateurness, if that's the appropriate word for it. The more efficient way to do that is to realize that c over x is the same as c times x to the negative 1. Right, that's the same expression. And then use the power rule. So the derivative of this, a constant attached to a function comes along for the ride. The derivative of x to the negative 1, the negative 1 comes out, right? And what do you do to the power? Minus 1. What's negative 1 minus 1? Negative 2. Now you can see this is the same answer, isn't it? This is negative c x to the negative 2. Right, negative 1 times c is negative c, x to the negative 2. And then if you drop the x down, you're back here. Same answer, right? Same exact answer? Two different ways of doing it. All right, any questions? Because I'm going to write down this derivative. Yes?
What I did is, on the bottom, is I got the
Common denominator. You could do all that too.
Do that?
Yep,
Okay.
yep. All right, so we have this equals, we said the top left was 1, right? 1 times this, so it's just x plus c over x, minus, and then the derivative of this, which is 1 plus, what? negative c over x squared, right? Either way you want to look at that. So negative c over x squared. Now I need that in parentheses because that was two terms, right? So there's my derivative. And then times what still? X. And then all of this over x squared. Questions? Oh, yeah, sorry. That's x plus c over x. Thank you. That would have caused some issues later. I don't know where I got that from. I think I looked back over here or something. I don't know. All right, let's try and clean this up. We've got x plus c over x. That's this. This right here, I can distribute the x through, right? X times 1 is going to be x, then take away, so minus x. And then what happens when I multiply the x times this one? Negative c over cx over x squared. So one of the x's cancel.
Yeah.
So you get negative c over x, but then minus. So plus c over x. And then all of this over x plus c over x squared. And those x's cancel. You can combine like terms. What's c over x plus c over x? 2c over x over x plus c over x squared. I'm going to guess that's not what they have in the back of the book. Right? They probably did more. I wonder how much further they went. Which one was this? Okay, I'll show you what they did. The answer in the back of the book is 2cx. The answer in the back is 2cx over x squared plus c squared. That's the answer in the back of the book. And this is our answer so far, right? So let's see if we can get to their answer. So they probably put this together with a common denominator first. This in here, right? Which would make it what? 2c over x over, in parentheses, squared what? These two together. This is over 1. You need an x top and bottom here, so x squared plus c over x squared. Now they did that so that they could try and free up, over x, right? They did that so they could now apply the square to the top and bottom separately. So what happens now is you get 2c over x over square the top. So I'll just write x squared plus c squared, and then square the bottom and you get what? X squared. And now if you flip this fraction up like this, right, you'll get the x squared up here, and down below you'll get the x squared plus c squared. And now that's gone, right? It's all gone. And do you see that this x squared and this x, they cancel out? You lose one x, and then you have 2cx over x squared plus c quantity squared. So really, again, you should be going to try and turn your answer to the back of the book. That's how you'll get better at the algebra. Don't look at your answer and be like, man, I'm so off. You know, usually you're there. It's just that you got to do some manipulation first. All right. Well, today is an important day. We're going to talk about the chain rule, which is the most important rule when it comes to derivatives. This is 2.5, yes. Did I say something else? No, okay. This 2.5 chain rule. The lecture notes that I have for this are like a page long. There's not much to it because you got to see this thing in action. So what are the rules that we have up to this point? Power rule, right? Power comes down. Product rule, quotient rule, right? And now what we need to do is come up with a rule that will allow us to handle something we have avoided up to this point, which is composition of functions. You know, up to this point, if we add functions together, we can take derivatives. If we subtract them, we can take derivatives. If we have a product of two functions, we can take derivatives. If we have a quotient of two functions, we can take derivatives. But what about a function that's inside of another function, like composition? So let me give you an example. What if you have something like f of x is sine of x squared plus 1? See, that's not a product, is it?
No.
It's not a product. That's composition. How do we know it's composition? Because when you say this, you say what? Sine of x squared plus 1, right? You don't say sin times x squared plus 1. You say sine of. And anytime you're saying of, that's the composition part of it, right? A function inside of a function. So how do we handle this? How do we handle a function inside of another function? So here's let's call this capital F, just so we can change up some of the notation here. Back when we were learning composition, we were able to say something like this. When we said f of g, or fog, or whatever, if you've heard that, f of g of x meant that what you're going to do is you're going to take the variable x, you're going to plug it into a g function, and you're going to take that g function, you're going to plug it into an f function, right? In this particular example, what would be the g and what would be the f? You tell me. So f of x would be what function? Sine function. And g of x would be x squared plus 1, right? And that way, when you take g and you take that entire expression, you plug it in right there for that x, you get back that capital F, right? That's what it is. So how do we handle something like this? Well, here's the chain rule. Here's what it says. The chain rule says that if you have, let's say, capital F is equal to some little f composed with some little g, right? So we have a composition of two functions. Then the derivative of capital F is the following. I'm going to move this down. It's the f function, okay? You take its derivative, and inside of it, you plug in the g function without a derivative on the g function. Then you multiply. This is where the chain comes in, okay? So this is the first link of the chain. The next link of the chain is you go inside you've already taken the derivative of f. Now you go inside and you take the derivative of the g function and you tack it on to the end with multiplication. That's the chain rule. So let me walk back through it again with you, and then we'll apply it, and then hopefully you'll see it. All right, so if you have composition of two functions, you first have to be able to identify which is f and which is g. And then what you'll do is you'll take the derivative of f. Inside of that, you're going to plug in the g function untouched, no derivative. When you're done, you will multiply times the g function, but after you've taken the derivative. So let's see it on this example, and then we'll start getting more complicated problems. So for here, put it up here. Everybody tell me what, since we already wrote this down, what is f prime of x? What's the derivative of f? Cosine of x, right? Well, if the derivative of f is cosine of x, in the chain rule, I want to take that derivative and plug into it what? G of x. So tell me what the derivative with g of x plugged in would be? It would be cosine, but the g function in there instead of just x. So I'm taking this g function and I'm plugging it in to the derivative of the f function. Do you all see that? That's just this part. Then what am I supposed to tack onto the outside? The derivative of g. So let me write down what the derivative of g is. It's just 2x. Okay, now I'm going to write the answer. Okay, that was just me getting all my information together. So the derivative of f, capital F, will be cosine of x squared plus 1, then what? Times 2x.
Would you still want us to apply that to 2x?
Yeah, that's exactly what I was going to say next, is that you should also get into a habit of pulling that 2x out in front so that you don't accidentally confuse yourself and then distribute that through. You can't touch this stuff because it's inside the cosine function, right? And that's it. That's your answer. Yes?
So if we were to have to find a derivative of where there's a square root, the square root would be the f of x.
Yeah, let's do one. Yeah, let's do one. Yes?
Would it still apply down, like, how would it be if you had f of g of h?
Yeah, what happens if you have three functions,
Yeah.
right? Okay, we'll address that also. Yep. All right. You ready? Keep going. Let's do another example. When are you coming by? When are you supposed to? Thursday. Okay. All right, next example. Let's take y equals square root of x squared plus cosine x. So just listen to yourself say that. Y equals the square root of, right, x squared plus cosine x. That of in there is almost leading you to the idea of composition. You have something, a function inside of another function. But we have to get the order in which these are occurring correct, okay? Because there is what we refer to as an outer function and an inner function. The outer function is f, the inner function is g. So in this problem, the outer function would be what? Square root of x. The inner function would be x squared plus cosine x, right? If you take this and plug it in right there, you would get that, and that's the composition together, right? All right, so according to the formula, I need to take the derivative of f and plug g into it. So let's just find the derivative of f first. What would the derivative of f be? So depending on how you've got this memorized, remember this was one of the ones I told you you should just spit that out. 1 over 2 root x. That's the derivative of the square root of x. If someone were to say to me, it's 1/2 x to the negative 1/2, I would say, yes, you're correct. But this is the way that you should remember it. It helps a lot later on, just being faster at this. All right? That's what the derivative of f is. Now, since we've got the derivative here, would you like to go ahead and plug g into it now? Okay, so I'm trying to get this first piece right here of the chain rule. So the f prime, I'm going to plug in g of x into it. So that's what? 1 over 2 square root of x squared plus cosine x, right? That's this part, right? So I'm taking this derivative, but inside of it, the x, instead of putting x in there and plugging in g, what was g? G was this. The next piece of information that I need is the derivative of g. And the derivative of g is, well, 2x minus sine x. So derivative of x squared is 2x. Derivative of cosine x is negative sine x. Done. So now we can put it all together, can't we?
Yep.
All right, so our derivative will be y prime will equal this piece right here, 1 over 2 square root x squared plus cosine x, times, it's always times in chain rule, not plus, the derivative of g, which was 2x minus sine x. Now, is that correct? Am I missing something? What do I need?
Put it 1 over and just put it together. I'll put 1 underneath it and put it together.
Yes, but I need to remember that that's a parenthesis around there, so the whole thing could go up top, couldn't it? So you could put here 2x minus sine x over 2 root x squared plus cosine x. And I'm not proving to you the chain rule. And to do that, I would have to prove it using the limit definition, and that one's it's an interesting proof. It's actually, I believe, in the book.
There is.
Yeah, there is some sort of proof. It's not the precise proof, but it is a sketch of the proof.
Actually, at the very end, I think it does.
The
actually
appendix, or no, at the end of the section they do it? Okay. Oh yeah, they have the proof there. It's still pretty complicated though. All right. Questions? Do 2 more and then I'm going to show you something else. I would like for us to look at y equals sine squared x versus y equals sine x squared. The difference between these two is where the squaring is happening, right?
Yep.
So you need to determine if, first of all, is this chain rule? Well, is that a product?
No.
No.
It's something squared, isn't it? Something squared? In fact, this looks more like, if we write it in a different notation, this is sine x, the whole quantity, right, squared? As opposed to this one, the squared is inside, right? So this is sine of x squared. This is sine of x squared, right? Did I say the exact same things? This is sine of x squared. This is sine of x squared. I said the exact same thing, right? It's the emphasis of where the squared is. So we'd say sine of the quantity x squared. This we'd say sine of x, that quantity squared. So there's some trickiness in that. But these are going to be completely different f's and completely different g's, right? So let's look at these. On the one on the left side, what would the f function be, and then what would the g function be? So we want to think about composition as being like an onion with layers to it. You have an outer layer, and then the layers go into an inner layer. Right now, we're just dealing with an outer and an inner because we've only looked at composition of 2 things, f and g. So what?
X squared.
X squared is what?
F.
Wait, x squared is f? Something being squared? And then what? That would force g to be what? Sine of x. So let's see if you agree with that. If I take sine of x and I plug it in right there, do I get this? Yes? Let's compare that to this over here. Here, what would be the f? Sine of x, and the g would be X squared. So now if I take x squared and I plug it in right there, I would get this. Do you see the difference between the two? No questions? So let's work this information out over here, because these are two separate problems. The derivative of f, we need to know what that is. In this case, it's what? 2x. What is the derivative of f with g plugged into it? 2 sine of x, right? I'm taking this 2x and I'm replacing the x with g. G was sine x. So this is 2 times sine x. What else do I need in this to finish off chain rule? I need g prime. G prime of x would be what here? Cosine x. You with me? Now that's not our answer, right? That's just our work. So the derivative, when we write it down, I'll put it up here. The derivative on this one, y prime, would be equal to this one right here, right? 2 sine x times cosine x. And that would be the correct answer, 2 sine x cosine x. Although this would also be a correct answer. And that's just using the double angle identity from pre-cal. 2 sine x cosine x is sine 2x if you go back to pre-cal and look at your formulas. All right, so let's compare that to this one. For here, we need the derivative of f, which is, in this case, what? Cosine x. We need the derivative of f, but we need to plug in g into it. So take your g function, plug it into the derivative, and what would that be? Cosine of x squared. We also need the derivative of g. What's the derivative of g? 2x. And so with that, I should be able to write out the answer. Yes? So the derivative of y should be, you tell me. You want to write that one? Well, let me write it this way first, and then I'll write the 2x out front. This, right? That's this, and then times 2x. And then you put the 2x out front, cosine x squared. Very different answers, right? Very different answers.
You take off and put in parentheses.
Put what in parentheses?
X squared on the right.
That is why we write this when we want to square cosine. That's why we put the 2 here, so you don't accidentally think it's the 2 out there. So if you were to put 2 here, everyone should understand that you mean to square the x. But if you don't want there to be any confusion, then just be safe and throw it in parentheses. Okay. Question?
There's a little bit easier way of doing it than all that work, though, isn't there?
There's a whole lot easier way to do it. But the problem with the easier way is that not everyone sees it. And so I need to show a method that will be a little more efficient for people who are having trouble with this method. They have more of kind of, okay, do this, do this, do this. If you go to a Cal 2 student, not a single Cal 2 student that would be asked to take derivative of this would write any of this information down. They would do it all in their heads, which is where you want to get, but it takes a little time for it. So I'm going to show you the shorter way, but after I finish up with this, all right? This is your fallback method. All right. What about a triple composition? What if you got a triple? So let's talk about what you think that might become. All right. So how about this? What if capital F of x is equal to f with g, and inside g is h of x? So now you have a function in a function in a function. 3 layers to the onion. What do you think the derivative is going to be? Well, last time we started with the derivative of little f, right? And what did we plug into that? Before it was just g. But now it's got more than just g in it. It actually has g of h of x. So it's the same story. You take the derivative of f. Inside of it, you plug those other two layers of the onion that have not been differentiated. Then times, what do you think? G prime, what do you think goes in G prime? H of x, no derivative, right? And then times h prime of x. So do you see how you're going from the outside of the onion inside? So you start on the outside layer, you differentiate that outside layer, you leave everything else alone, plug it in. Then times next layer derivative inside of that, and then last layer derivative. Everything with multiplication. What if we had 4 functions? We'd have an additional piece out here, right? Okay, so let's see if we can do an example of this. What about if you have y equals sine of x squared plus 1? Sine of, I've got 2 compositions in there, which means I have 3 functions, right? So what is the outer layer of this onion here? The outer one is this sine, right? So f of x is sine x. What's the next layer of the onion? Sine x again. And what's the final layer of the onion, the h? X squared plus 1, right? Now keep in mind, this piece right here, isn't that g of h of x right there? Isn't that what that is? That's g of h of x? That's g with h plugged in. Now the reason why I'm writing that down is because don't we need that right in here? And then h of x, I know what h of x is, and then over here the derivative of h I'm going to get in a second. So here we go. Let's find the derivative of f first. What's the derivative of f? Cosine x. Now what is the derivative of f with g of h of x plugged into it? Cosine of this, sine of x squared plus 1. I know it starts to look like a parentheses nightmare, but do y'all agree with that? Now I also need g prime, don't I? Okay, what's g prime of x? Cosine of x, right? That's g prime of x. But I need g prime of h of x. So what's g prime of h of x? Cosine of x squared plus 1. And then lastly, I need what? H prime of x, which is just 2x. So you see I'm getting all the pieces together here, and then I'm going to put them all together in my final answer, which is going to be the chain of derivatives. So in this problem, y prime would be equal to what? This piece first, right? This piece right here. Cosine of sine of x squared plus 1, close, close, times g prime of h of x, which is cosine of x squared plus 1, times h prime of x, which is 2x, which I could throw out to the front, couldn't I? That would be it. This can become a little tedious, as you can see, right? I mean, can you imagine? Any questions? What do you think the secret is to getting good at this? Practicing it, yeah. So it's not so much of a secret. You all knew the answer.
So you're still only gonna have two?
What's that?
You're only gonna have two?
Two, but then you have to do the product rule.
Yeah, I have composition because I definitely have like tangent of something, right? And then the cubed is really like saying something cubed. That's the cube is a function, right? But the inside here is not composition, it's a product. So we actually have a product rule combined here with the chain rule. So let's see if we can just first decompose this thing into different functions and then apply the chain rule. But in terms of an onion, what's the outer layer of the onion? The cubed, right? So to help you figure out what's the last or outer layer, just imagine if you were to actually plug a number in. Okay? If you plug a number into this, the last thing you do is the last function. So like if I plug in a number like, whatever, pi or 2 or something, figure out what this is first, right? And then I take tangent of that, right? And then I cube that answer. So the cube is the last thing happening, so that's your outer function. That's the little f. So little f of x here is what? X cubed. Okay, what's the next layer in? Tangent of x. And then the next layer in is not a composition, right? But it is something, right? H of x would be x sine x, wouldn't it? I will need all three derivatives, won't I? So let's start with the first one. F prime of x is 3x squared. Then let's look at what f prime with g of h of x is. So what, 3? But then what squared?
Tangent squared.
What's being squared? G with h plugged in, right?
Tangent of x sine.
So tangent of this. Tangent of x sine x. All of that squared. Now I could put that squared here on the tan, right? Couldn't I?
Yeah.
But I'm just doing this just to help you see this is 3x squared. That's this. So that's part of my answer, isn't it? All right. So I also need the derivative of g. So what's the derivative of g? Secant squared x. And what is the derivative of g with h plugged in, but not the derivative of h? Secant squared of x sine x. And there's one more thing I need to be able to put my answers, the second part of my chain.
So you have to apply the product rule.
The derivative of h, right? I'll put that up here. The derivative of h. But the derivative of h requires a product rule. Right? So it's going to be sine x plus x cosine x. Derivative of x is 1 times sine x. Derivative of sine x is cosine x times x. I pop the x out in front. Pretty much from this point on, if I'm doing a product rule like this, I'm not going to go through the actual setup anymore. I'm just going to write it down.
on a test? Do you want to see it all worked out?
If you're comfortable with the product rule in your head, then go ahead. But I don't want to see you pull out the TI-89 and take the derivative and just write down the answer. I need to see something. All right, ready for an answer? And put this all together. So it's going to go right, I'm going to put it right underneath this. Y prime is equal to 3 tangent squared of x sine x times, right? Secant squared of x sine x times sine x plus x cosine x. I need this in parentheses because it's two terms. So that last piece has to be in parentheses. All right, just a quick show of hands. How many of you feel like you kind of got the idea of how this works? Yeah? All right. We could, of course, do composition of 4 functions. We could do things, crazy shit like this, where we're like sine square root of cosine of x over 1 plus sine squared, oh no, let's make it minus sine squared of x plus 1, whatever. So you've got what? Quotient rule, right? But the top left is a chain rule. And so you got to go figure out that chain rule before you come back, and it could become a disaster, but we have a way of doing it, right? We do.
Is there like an order of operations when you're doing with something?
With this, quotient is the overruling thing. So you set up your squared, right? You set that up. Top left corner is this problem, which is its own problem now. You go do that, get the answer, it's ugly as shit, and you come back here and you plug it in right there. And then you do this, and then this is the derivative of the bottom, but wait a minute, that's another chain rule right there, and you figure out all that, and you plug it back in, and then you hope you can clean that up a little bit. But at least you get the derivative, right? At least you get the raw derivative. That's beyond what I would give you on a test or something like that. Okay, now, let's talk about the shorter way to do it, right? Where you don't have to write down what's F, G, and H and then come up with chain rule. And we'll just kind of see how this goes, all right? So we'll start with this example. All right, we talked about the onion, the layer, right? Everything else. So what was the outer layer of this onion? X cubed. So I'm bringing my magic cloth here. This is my magic cloth. All right? And so at the end of the day, my cloth is not long enough. I really have like a cloth to the third power, don't I? What is the derivative of a cloth to the third power? 3 cloths to the second power, right? So the derivative should be 3 cloths squared, yes? What was the cloth, though? Tangent of x sine x, right? Yes? So you have taken the derivative of the cubed layer, right? So you have exhausted this, you're done with that, no need to look at that anymore. What's the next layer in? Tangent of my eraser. The derivative of tangent of an eraser is secant squared of an eraser. Secant squared of an eraser, which my eraser was x sine x. So now you've exhausted the tangent, haven't you? And now you look here and you say, that's a product rule. Derivative of that is what? Product rule. Sine x plus x cosine x. Right? That's the same answer. So sometimes I've taught this class for so many freaking years that I've shown this to start and then shown the shortcut. I've taught a class where I just showed this and never showed the other way. I've done just the other way, not this. I don't know. It depends on the student, you know. How many of you followed that? Okay. Let's go back and do all of them, the ones that we already did. They should be pretty clean. What was the one before this? Was the one before this where we were comparing the two versus? Okay, so let's just do one of those first. This one right here. Was it that? You remember what the answer was, right? It was 2 sine x cosine x? Okay, so you can bring out whatever magic thing you have, like your hand or your finger, whatever you're writing on there, right? The outer layer of this onion is squared, right? So cloth squared. The derivative of a cloth squared is 2 cloths, right? But the cloth was what? Sine x. Okay, times, because it's always times with chain rule. Now you've taken care of the 2. All that's left is sine. Derivative of sine x is cosine x. You're done. Does it seem a lot easier? Absolutely. If you follow it, it's much easier. All right, compare that to the other one. Y equals sine x squared. This time the outer layer was the sine, right? So you cover up what? The x squared. So the derivative of sine of my green cloth is cosine of my green cloth. The green cloth is x squared, right? Then times, now you've done sine. Take the derivative of x squared. It's 2x. Same result as before.
And so the work on the test will be shown by crossing out.
No.
Stuff, or
By the time you get to the test, I won't give you a problem like that, but you know.
But if it was.
But if it was, I really honestly wouldn't want a Cal 1 student to write anything but this. I mean, like, now if you need to do the F and the G and all that, then that's, you know, you got to do what works for you. But then it becomes a time issue, right? This derivative should take a Cal 1 student about 15 seconds to do. You know, right? I mean, 15 seconds maybe, if you're doing it this way. If you're doing it the other way, it's going to take about 2 or 3 minutes maybe. So this is the way I prefer, all right? Like I said, if when you get to Cal 2 and they throw that on the board and they say, all right, we need a derivative of sine squared x, you know, if you see someone writing down like f of x equals, if you see that, you get concerned, really concerned. They should just be like 2 sine x cosine x. But, you know, we have to walk before we run, right? Crawl before we walk. See a problem that should I stick with the shortcut? Stick with it for now? If people start falling off the bus here, you just got to let me know, okay? I want the derivative of this. So what am I going to use for this? Product rule. That's the overruling thing happening here is a product right there, right? And if you're going to use the product, then we know that we're going to need to be able to take the derivative of that. We're going to need to know that, right? And the derivative of this. This is just power rule, right? This is a little bit of chain rule, though, because you got something to a power, right? So let's see if we can handle this. According to the product rule, this will be the derivative of x squared times 2x plus 1 to the 999th power plus 2x plus 1 to the 999th power, whatever that derivative is, times x squared. So I'm writing out the product rule like in detail. I will at some point stop doing this. Can you handle the derivative of x squared? Sure. Derivative here? Uh-oh. I only have one of these, so if you need, you know, you can go buy yourself a green cloth if you need to. Right? You got that to 999. So we'll have to use the chain rule there. All right, so let's write it out. This is 2x. 2x plus 1 to the 999 plus